start with a brief introduction to chemistry. So, as a science, chemistry is really looking at atoms and molecules and how they behave. The goal is to be able to control how they behave, to make interesting new materials, and also to make really cool explosions. So atoms are going to be submicroscopic particles, so small you can't see them without a very specialized instrument. And they are the building blocks of matter. Matter is anything that takes up space or volume and has mass. So atoms are the building blocks that make up everything around us. And an atom existing on its own is pretty rare out in nature. Usually they bind together in specific arrangements and they form molecules. So we have atoms like carbon, oxygen, and hydrogen that don't actually exist on their own very often. But they combine in a ton of different ways to actually form the molecules that make up our life. Methane is a gas, water is the solvent of our life, and glucose is sugar. And these are all made up of the same three types of atoms: carbon, oxygen, and hydrogen. They're just different numbers of these atoms combined in different ways. So to study how matter actually behaves, we do also need to study energy as well. So within matter, we'll study atoms and molecules, but we need to be able to understand the energetics of these molecules and atoms. Within energy, there's two different types. There's potential energy, which is like being at the top of a roller coaster if you're in a physics class, and kinetic energy, which is racing to the bottom of a roller coaster down a hill in a physics class. But in chemistry, we think of potential energy as the energy stored in a bond between here an oxygen and a hydrogen atom. And the amount of energy that is stored in this particular chemical bond is about 490 kilojoules for every mole. We'll get into what those units mean later in the quarter. And when we talk about kinetic energy of molecules, we're really looking at the motion of molecules. They have translational motion where they move around a room or within a space. They can rotate and they can vibrate and stretch. And all of this counts as kinetic energy. So let's start by looking at matter. So matter, as I said before, is anything that takes up mass and volume. Some naturally occurring types of matter include cotton, sand, or a cardiac drug called digoxin that we can actually isolate from plants. We have synthetic types of matter: nylon, styrofoam, ibuprofen. These are all things that we develop in a lab. But these are all matter. And they're all chemicals, regardless of if they occur naturally or if they're synthetic. Pure substances we're going to define now as we classify the types of matter as having a very definite composition. Whereas a mixture is going to be made up of two or more substances that are not going to be chemically combined, but will be physically combined together. So these will make up our first two categories of matter as we try to classify it. So looking at pure substances, we can classify it as a pure substance if it's just one type of matter. So it's composed of all of the same things. So here's an example of aluminum. We have lots of aluminum atoms and it's just aluminum metal. It's a pure substance. And so this is an example of when we have just an element composing our matter, one element. A compound is something that's composed of two or more elements, like the water we saw on the previous slide. A water molecule is composed of oxygen and hydrogen. But if I have a sample of just water, it would be a pure substance that is actually a compound rather than just one element. So here's another example of a compound, table salt. Table salt is a combination of sodium ions and chloride ions. And we can combine our sodium and our chlorine in a very specific pattern in a very specific way, and it'll always be table salt. And if we have no other atoms or compounds involved, then we have a pure substance. Some other examples are hydrogen peroxide or sugar or water. Now, our second category of matter was mixtures. Now, mixtures are a type of matter that consists of more than one substance combined physically. That means that we can separate them by a physical method. And one example of that right here is filtration, where we use filter paper inside this funnel to separate out the liquid and the yellow solid, which will be left behind, that made up the mixture right here. And these two substances, this liquid and this yellow solid, can be combined in different proportions and still be a mixture. So within mixtures, we have two categories, homogeneous and heterogeneous. A homogeneous mixture right here is something that is going to have a uniform composition. It might look like a pure substance, and it's just that it isn't, you're not going to be able to differentiate between where your two different compounds are. And a great example of this is simple syrup, where you have sugar and water mixed together such that you can't actually tell where the sugar is and where the water is. It looks like one thing. Now, a heterogeneous mixture is going to be where our two compounds that we've mixed together don't actually mix in a uniform way. And so we get, it looks like you can visually separate them, your two substances. And here's the perfect example, which is vinaigrette, right? Which we have an oil and a water, or oil and a vinegar combined, and they don't actually mix in a uniform way. And so you get this layer right here, where you have your water in one layer and your oil in another. So here we can classify everything into one chart. Within matter, we can classify it as either a pure substance or a mixture. Within our categories of pure substances, we have either something that's just a pure element or something that'll be a pure compound. So it'll be one chemical combination of atoms. Here's an example of water. Within our mixtures, we have either homogeneous, where everything would be nice and uniform, and heterogeneous, where we would be able to actually see the two different components of the mixture. Here's an example of copper pennies and a glass of water. This is a mixture of two things, water and copper. Now we'll talk about properties of matter. So first, there's the states of matter. Matter typically comes as either a solid, a liquid, or a gas. And the difference between these three states of matter is really the amount of kinetic energy that the molecules have. So in the solid state, we have very low kinetic energy, which really means little movement from our particles. In the solid state, our matter will have a very definite volume. That means it will have its own shape. And it will keep that shape no matter where you put it, what container. Now, these particles are going to be really close together, and they're going to stay in a fixed position, a fixed pattern in the solid state. Now, once all of these particles, either atoms or molecules, have more kinetic energy, which remember is again the energy of movement, they'll be able to move around more and more, and these will now take on the liquid state. Now, in the liquid state, we still have a very definite volume, but our shape takes on whatever the shape of the container is. In this case, an Erlenmeyer flask. And these particles are constantly moving around each other. As they get more kinetic energy, the particles then will enter the gas physical state. Now, this doesn't have a definite shape, and it doesn't have a definite volume. It'll take up the volume of the container. So in this case, it's the entire Erlenmeyer flask. And there's a lot more space in between these particles. And they're moving around much, much faster within the container they're located in. So we'll look at both physical properties and chemical properties of our matter. And starting with physical properties, those three states that we just discussed, solid, liquid, and gas, are all physical states that our compound water in this case can have. And so when it changes from one state to another, like going from solid water to liquid water, it'll undergo what we call a physical change. That physical change here is going to be melting. If we go from water to a gas, from liquid water to a gas, we'll have the phase change called boiling. Again, this is another physical change. So things like the temperature that freezing occurs at and the temperature that boiling occurs at are what we call physical properties. We can observe them, we can measure them, as long as the composition of the matter stays exactly the same, that it's still water, it'll have the same boiling point and freezing point. It'll also have the same density, which will be its mass relative to its volume, the same color, shape, and again, whether or not it's a liquid, a solid, or a gas at a given temperature. So a physical change occurs if there's a change in state like we discussed, or a change to its physical shape. So that could be breaking an ice cube. And any other sort of change as long as there isn't any change to its composition. So in the example of water, everything that can occur, any change that occurs, that still keeps this water molecule intact for the substance. Here's an example of deposition. This is when we have a gas transitioning into the solid phase, and it forms these really beautiful crystalline structures that we call hoarfrost. Chemical properties. Now, this is different from physical properties. These are going to describe some ability of the substance. And we can observe this still, but it really is about how the substance is interacting with other substances or its ability to change into a new substance. So this might include things like flammability, toxicity, or reactivity. So how it changes into another molecule. And these are the same as the warning signs we usually care about for molecules. We care if they're toxic, we care if they're flammable, and we care if they're going to be extremely reactive with things like oxygen or water. When a chemical change is taking place, an original substance is actually turned into a new substance. And that new substance is going to have new chemical and physical properties. So you might see things like the freezing point of your new substance be different than the freezing point of what you started with. Or in this case with toast, we put in white bread into a toaster and it undergoes the Maillard reaction and it browns. And so we can see color change in our toast on the outside. We also notice a change in smell. And a change in texture. It's much harder. And so these are physical properties of our new chemical on the outside of the toast that's undergone this chemical change. So try this example problem, and in the following video, we'll go over the solutions. Try to classify these different changes as either a physical change or a chemical change.